This is our challenge problem from related rates. A 13-foot ladder is leaning against a house when its base starts to slide away. So I'm going to draw a figure of what that's going to look like. House, ladder, ground. Ladder is 13 feet. And the ladder starts to slide away. By the time the base is 12 feet from the house, so here's our base, 12 feet away from the house, the base is moving at a rate of 5 feet per second. So that means dB dt, or the rate of change of the base, is 5 feet per second, but the ladder is just, it's like sliding away like this. I'm going to put the units feet per second. Okay. Whereas the 13 and the 12 are just measurements. What we want to know is how fast is the top of the ladder sliding down the wall. So that means we want to find this, which is dH dt. Okay, and then after we find that, we'll find the rate of change of the area, rate of change of theta, but before we do anything, we need dH dt. So, one thing that would be helpful to know is right now we have the 13 as a constant, the base is 12 at the time that we want. It would be nice if we could find h at this time. The way we're going to find that is we know that this is a right triangle, so we can set up the Pythagorean theorem, which would be the two legs added together, their squares added together equals the hypotenuse 13 squared. So b squared plus h squared equals 13 squared. Okay, and then we know what b squared should be. That's going to be 12 squared plus h squared equals 13 squared. We're trying to solve for h, so 144 plus h squared equals 169. Subtract 144 from both sides and we get h squared equals 25. Square root and h is 5. So the height at this time that we care about is 5, but we still don't have dH dt, how the height is changing, we just have the height value now. So now the only equation that we have that relates these two variables is that same one that we used to find the height. So all that we know is that b squared plus h squared equals 13 squared. Since we don't know anything about the area right now, we don't want to use an area formula, we just want to use this Pythagorean theorem. So let's take the derivative of this with respect to time. Okay, derivative of this first part using the power rule would be 2b, but since the base is changing with respect to time, we also need to write dB dt. Plus, derivative of h squared would be 2h, but again, this is changing with respect to time, so dH dt. And then the derivative of 13 squared, well, that's a constant, so that's just 0. So here's our formula, and now we're going to plug into it, where dH dt is the only thing that we don't know here. We know dB dt is 5 feet squared per second, or 5 feet per second. dH dt we don't know yet, so I'm just going to rewrite that. Okay, and then we know that the base at this time is 12. I'm going to plug that in here. So 12 times that. We know that the height is 5. So I'm going to plug in 5 right here. And then those are plugging in all the things that we know, so now I'm just going to rewrite the rest of the equation. So we have 2 times 12 times 5 plus 2 times 5 times dH dt equals 0. And then now we want to solve for dH dt. So this would be, this is 120 plus 10 dH dt equals 0. Subtract 120 from both sides. We get 10 dH dt equals negative 120. Divide by 10 and we get dH dt equals negative 12 feet per second. So this means that the ladder is sliding down the wall right here. It's going down the wall at a rate of 12 feet per second. So the negative just means that our value is going down. Okay, so now that we have dH dt, that's the first part of the question, we want to know at what rate is the area of the triangle changing. So to do that now, let's use the area formula. So area of a triangle is half the base times the height. And then we're going to find the derivative of this with respect to time. On the left, that's going to be dA dt. And then on the right, we need to do the product rule. So half, I'm going to keep b constant for this first one and take the derivative of h, which would be dH dt, plus half. Since last time I left b constant, this time I need to leave h constant, so that means take the derivative of b. So dB dt times the constant h. Okay, and then let's plug in everything into this formula. So half the base is 12, dH dt we just found is negative 12, plus 1/2 dB dt we know from the beginning is 5, and the height at this time is also 5. So we end up with half of a negative 144, so negative 72, plus half of 25 is 12.5, and we get negative 59.5. This is area, which is feet squared, so this rate of change would be in feet squared per second. And this is dA dt. So the rate of the change of area, the area is also decreasing at this time as the ladder is sliding down the wall. Okay, the last part of this problem asks us to find at what rate is the angle theta, which is the angle between the ladder and the ground right here. At what rate is that changing? So let's try to write some formula involving theta. So I'm going to choose sine of theta. The formula for sine of theta in a right triangle, so if we're doing right triangle trigonometry, is the opposite side divided by the hypotenuse side. And the opposite side is a variable. So the opposite side is h. But the hypotenuse side is the ladder, which is a constant, so that's 13. Okay, and now this is a formula for theta that involves theta. A different formula we could do would be, we could do cos theta, which is the adjacent side over the hypotenuse. That would be 12 over 13. I'm sorry, not 12 over 13. The base over 13, since it's a variable. Because we know that the base is also changing, so it needs to be included in our formula, even though we know what it is at the time we want. And we could even use for our formula, we could use tangent of theta, which is the opposite side over the adjacent side, so that would be h over b. We could use that. You don't really want to because it has an h and a b in it, so the sine and cosine formulas are simpler. So both of these are okay, but let's just use sine of theta. Okay. So for a theta problem like this, we're just looking at some way that we can compare theta in an equation to the h or the b or the 13. Okay, let's take the derivative of this. So derivative of, we're using this sine theta one. So the derivative of sine theta with respect to time would be cosine theta. And then by the chain rule, now multiply by the rate of change of theta, so d theta dt, equals, the 1 over 13 is just a constant, so we don't need to do the quotient rule. We just take the derivative of the height, so dh dt, and then we just have this 1 over 13 constant here. So I'm going to write that separately. Now we know a couple of things here. We know that dh dt is negative 12, so negative 12 times 1 over 13. That's what we have over here. And what we're trying to find is d theta dt, but we still have this other theta in the equation. We have cos theta here. So if we look, cos theta, at this time it's adjacent over hypotenuse, and at this time the adjacent side is 12. This base right here is adjacent to the angle. So we can, instead of cosine theta, write 12 over 13, the trig ratio that goes with cosine. So now we have 12 over 13 times d theta dt equals negative 12 over 13. Could divide by this, 12 over 13. It's better really to think about multiplying by the reciprocal, but that's fine. So divide this by 12 over 13, and we would get negative 1. So that means that d theta dt is equal to negative 1 radians per second. So that's how this angle is changing. Kind of the crucial step for this one that makes it a little harder is knowing to set up a trig equation to find this theta, and then also knowing that we can replace cosine theta with the side ratio that goes with cosine.